All right, so let's see how we can arrange the electrons using the orbital electronic configuration. Okay, so in order to understand this, let's look into a hypothetical situation of an Olympic Games city. Okay, so let's assume that your city is hosting the next Olympic Games. Pretty interesting, right? Okay, so if the games are being hosted in your city, you can expect a lot of guests, a lot of tourists who will be coming to your city. Where are they going to stay? In hotels, right? Pretty simple, like where will they stay? In hotels. Now, what a tourist, the first tourist that comes to your city would want to stay in a hotel closest to the Olympic Stadium. So let's assume this is the Olympic Stadium and these are different hotels. So it's a pretty detailed diagram in which we are trying to see that, okay, all these different rows that you see. So for example, so this row that I have demarcated is like a hotel. This is another hotel. This is another hotel. This is hotel number 1, hotel number 2, hotel 3, 4, 5, 6, 7, 8. Now, these hotels are arranged in increasing distance from the stadium, right? So these are increasing distance from the stadium. And the different hotels have different types of suites in the hotel. Now, we have a suite S in which there is only one room. Pretty lame suite. But the good thing about it is that it is closer. Like, so 1S is pretty close to the stadium, okay? Another type of suite that we have is a suite P in which we have 3 rooms, okay? Suite D, we have 5 rooms, and suite F, we have 7 rooms. Each room will house 2 guests, okay? So let's count the number of guests that can get into the S suite. S suite has 1 room and each room can get 2 guests. So the total number of guests in here in an S suite is 2. For the P, we have 3 rooms. Each room can have 2 guests. So the number of guests are 6. For D, it's 10, 5 times 2. For F, it's 14, 7 times 2. Pretty simple, right? Okay. Now, let's assume that the orientation of the hotel is something like this. Like you have S on the first floor, P on the second floor, D suite on the third floor, and F suite on the top floor, okay? So, let's now see how the guests start filling up in the city. Now, if there is one guest, the first guest that arrives to the city, can you imagine where that guest will go? It's very simple, right? That guest will try to check in to hotel number 1, and since hotel number 1 has only 1 suite, that guest will go to hotel 1 suite S. So that guest goes to 1S. A second guest arrives. The second guest or the second tourist will also check into the same 1S suite because that suite can hold 2 people and it's a crowded city, right? So you cannot afford to lose room space. Like the room space is limited. So the second guest also comes to the hotel 1 to hotel 1 in suite S. Now what happens to the next guest, the next number of guests that come? 1S is full, right? So we had S was only had 1 room and 2 guests are already inside the hotel. So the third guest that comes is going to check in to 2S, okay? And that is why I have these arrows. Now, if you see the arrows move in this direction, like so the arrowhead is here, this is the tail. So imagine that these arrowheads are going to tell the guest which is the best suite to occupy given the situation in the city. So the first one goes here. The second set of guests will try and see if you have vacancy in 2S. The next one comes and they will try and get into 2p, right? Because 1s is full, 2s is, if 2s becomes full, the next best room is 2p. The next best rooms are 3s. The next best suite is 3p, and then 4s. The next is 3d, 4p, 5s, as you see with the direction of the arrows. The best arrow is this, 1s. The next is 2s. The next is 2p, 3s. The 3p, 3s. Then 3d, 4p, 5s. Just follow the arrows, right? Right? Just follow the arrows. So this is the order in which these suites are going to get filled. Okay, now let's take an example in which there are 19 guests checking in the city. Now, the first 2 guests are going to go to the 1s, right? So I write 1s 2. Okay? Where are the next guests going to go? After 1s, you have 2s. So the next guests go to 2s. The next, to 2p, how many guests have been taken care of? 10, but you have 19. So what happens after 2p? You go to 3s. How many in s? How many in s? 2. How many in p? 6, right? You go to 3s2. How many taken care of? 12. Remaining 7. So after 3s, you go to 3p. 6, right? So you have 18 taken care of in here. 10 and 18. How many remaining? 1. So what happens to after 3p? 4s. So this is the configuration in which the guests are going to enter the hotels in the Olympic City. Now, as I said before, that this is hotel number 1, hotel number 2, hotel 3. So how many guests in hotel 1 in total? 2. How many guests in hotel 2? 8. How many guests in hotel 3? 8. And how many guests in hotel 4? 1. Does this look similar? 2, 8, 8, 1? Of course it does. This is similar to what we saw in here, 2, 8, 8, 1. So, if you have the orbital configuration, you can easily find out the number of electrons in the different shells. Why? Because the hotel is basically the orbit. Okay, so if you arrange things in the different orbitals, the suites being the orbitals, so this is the s orbital, this is the p orbital, this is the d orbital, this is the f orbital. So this is 1s is the s orbital of the first orbit. 2s is the s orbital of the second orbit. 2p, the p is the p orbital of the second orbit, and so on and so forth, right? Just for the sake of analogy, right? So you want to calculate the number of electrons in the shell, you first arrange this in terms of the orbitals, and then just calculate the number of electrons in the different shells. Now, why is this important to get into orbitals? We'll see shortly that when you try and arrange this in terms of the orbitals, many different things about the atom or the ion becomes clearer. Its stability, the reactivity of different elements, and comparisons of different, like which element is or which ion is more reactive than the other. Why does sodium have only Na plus? Why does Na doesn't have an Na2 plus, or why oxygen takes a O2 minus? Things like these. So many things will start becoming more clear and make sense when you understand and when you try and arrange the electrons in an atom using the orbital configuration that we have just discussed in here. Okay, so this is one of the very basic, very fundamental concepts in chemistry, and we should try and understand this very clearly, because this is going to make chemistry more fun and this will get us to a point where everything in chemistry can be tied to this simple concept. Okay? That being said, let's assume, let's try and arrange, find out the electronic configuration of lead-82. Lead-82 was really difficult to do in the orbital, in the orbit, the KLM shell configuration. Now let's see whether the lead in here is easier to do in the orbital configuration. Okay, let's start. So we have a long number of guests to fill in here. So let's start with, you keep your eye on here. So okay, you have 1s2, then we go to 2s, 2, we then go to 2p, so 2s, then you go to the next arrow, which is puncturing 2p first, so you fill 2p first, and then go to 3s, then go to 3p, because after 3s you come to this arrow, this punctures in here, 3p, go to 4s, 3d, 4p, 5s. Now let's calculate the number of electrons that are already being taken care of, the number of guests. Okay, so this is till here we have 10, we have 18, we have 20, 30, 36, 38. So we just have 38 electrons taken care of. We have a long way to go, so we keep moving. So after 5s we have 4d, so we have 4d10, so this becomes 48. Okay, so after 4d we go to 5p, 4d then 5p, we have 6 in p, 6s, 2, right? So 38, this is 48, 50, 56. So we have 56 taken care so far. We have 6s, then we move to 4f. So the maximum number that F can take is 14, because you have 7 rooms in the F-type suite, each takes 2, so maximum of 14. So we calculate the total number taken care of in here, 56 plus 14, 70. So 70, so far we have 12 more to go. So after 4F we go to 5D, D takes 10, and 6p takes 2. Okay? Now, let's arrange this so that we have all the number of hotels, like the orbits, together. So we have 1s2, 2s2, 2p6, 3s2, 3p6. We have a 3d in here. I write 3d. Then we move on to 4. We have a 4s here. Then we have a 4p. Then we have a 4d. We have a 4f. Then we move on to 5. We move on to 5. We have a 5s2, we have a 5p6, we have a 5d10, 5 is all taken care of. We move to 6, 6s2, and 6p2. Okay, now let's see, convert this into the orbit configuration, right? So in here we know that this is the K shell, because hotel number 1 is basically K, right? N equal to 1. So K gets 2 electrons, okay? This is L shell, L gets 8 electrons. M shell gets 18 electrons. Okay. F shell gets 14 plus 10, 24, 24 plus 6, 30, 30 plus 2, 32, 5 gets 16, 10 plus 6, 16 to 18, 4. So what is the configuration that you get finally? So you get a 2, 8, so this is K, this is L, M is 18, N is 32, O is 18, and P is 4. Now let's match this with the electronic configuration that we saw earlier. Okay? So 2, 8, 18, 32, 8, 4. I don't know if you can see that. So this is 2, 8, 18, 32, 18, 4. 2, 8, 18, 32, 18, 4, right? So this was complicated, but doing this was not, because we followed a typical order of filling in the orbitals, and we got to a point that we have all the 82 electrons separated in the different orbitals. Then we arrange the number of the different orbitals in terms of their hotel numbers or orbit numbers, and we sum these different electrons and we get this. So it's easy to get this and then convert this into this, but the opposite is not true, right? If you have this, it's not possible to convert this into this, but the opposite is true. In here, you can have an orbital configuration and convert this into orbit, and having this gives you more information about how the atom is, how the electrons are arranged, and we'll see how that solves many of the problems in chemistry ahead.